Hello, good morning. Later, we are going to cover linear vector spaces. It must be understood that most operators in quantum mechanics are linear operators. And we are very fortunate because it allows us to represent quantum mechanical operators as matrices and wave functions as vectors in some linear vector space. Therefore, it becomes quite indispensable for us to understand these abstract objects, or you can say abstract algebraic structures called as the linear vector spaces. So before we start with linear vector spaces, let us start with something that we already know. See, what is R? R represents a real number. R represents any real number on a real number line. So for example, if a number is positive, it lies to the positive side of 0, on the right hand side of 0, and if the number is negative, it lies on the negative side of 0, that is the left hand side of the 0. So in order to represent a point on real number line, in order to represent a number, a real number, we try to go and see what is that point and what is the location of the point on the real number line. So there is a one-to-one correspondence between the point on the real number line and the number itself. So you tell me a point, I will tell you I'll tell you the location of the real number line. Similarly, if I want to find an ordered pair, let's say I say where will be the location of 3 4. Instantly you're going to make a two-dimensional space and you're going to say me, okay, this is 3, this is 4, so this is going to be 3 4. So in general, if I say that all xy belongs to R square, if I take all these values, that is x belongs to R and y belongs to R, what do you think? Where all these values will be represented? All the values will be represented on the plane. So basically, what does R square represent? Your R square represents a Cartesian plane. Okay, and most of the in fact, the two-dimensional geometry is done on this particular space. That is, whenever you declare some vector, let us say two-dimensional vector, you say that my velocity vector is, let's say, 2i cap plus 3j cap units, whatsoever the units may be. So what does it represent? It represents that along x-axis the component is 2, along z-axis the component is 3. Whether you write this way or you write this way, this is one and the same thing. Similarly, if I want to write R cube, what does it represent? It represents me a volume in the three-dimensional space, and it in fact represents the entire volume. Whether you draw it using this, that is, all these x's are going towards infinity, and it's just one of the spaces. So basically, it is just one of the spaces. In general, what does R cube represent? R cube represents the entire volume. Not only this, the entire volume. So you can represent in this manner, you can represent in this manner as well. An ever extending sphere, it's not two-dimensional, mind you, this is three-dimensional. So ever extending sphere, or you can say a ball in three dimension, so it would actually cover all the R cube, Now let us understand a few things that we have studied in our standard 12th, and from there we are going to take inspiration, and we are going to write the definition of linear vector space, and certainly after that particular thing you will be able to understand how this particular definition uh, is like how this particular definition is it's feasible. Okay, so let us see. Okay, Okay, so see, now I'm going to start with r square. Okay, I'm going to start with r square, and from there you will be able to. I hope everybody is aware of the basic vector algebra from standard 12. So that I'm not going to do, but I'm going to just start with r square as a space. So let us discuss r square. I already told you what does r square represent. R square represents your Cartesian plane. R square represents your Cartesian plane. Okay. Now you see in R square what sort of things that you can do. One of the things that you can do, and what notation I'm going to take. Let's say if I'm saying x I cap, x1 I cap plus y1 j cap. Instead of this, I'm going to write this way. Okay. So this is the notation I'm going to use. Okay. So if say if I take two plane vectors, let's say x1 and y1, another plane vector x2 and y2, how do I define the addition? How do I define the addition? So addition of these two vectors would be defined this way. Okay, this is how I'm going to define the addition. That is, in the space, if I have this vector x1 comma y1, let's say this is my x1 comma y1, and let us say this is my x2 comma y2. So what I will do, if I want to add, I'll use the parallelogram law of vector addition, and I'm going to add. This is again, here it is. So let's say this is your x1 comma y1, and let us say this is your x2 comma y2. Then this would be what? This particular point would be your this point, x1 plus x2 comma y1 plus y2. Okay, so one of the operations that you can do on two-dimensional space, that is on R square, that is with respect to two plane vectors, let's say x1 comma y1 and x2 comma y2. These are the two plane vectors. Okay, I can do this kind of operation, isn't it? This is something that you know from your standard 12th. Another operation that you can think of is called as a scalar multiplication. Another operation that you can think of is called as a scalar multiplication. So here it is, scalar multiplication. Why I'm doing this? From here we'll take a motivation, and then you'll be able to familiarize yourself with the definition that we give for the linear vector spaces. And as I told you, linear vector spaces are quite important. Actually, in the very initial, I mentioned that most of the operators in quantum mechanics are the linear operators. And these linear operators, fortunately, can be represented in terms of the matrices, especially Hermitian matrices. And wave functions in quantum mechanics can be represented as vectors. So therefore, it is quite indispensable for us to understand what are linear vector spaces in general. So today we are going to study with this only, and as I have started with a definition. I have started with a particular space, a linear vector space itself, that is R square. Without telling you that this is a linear vector space, I have started with something called as I have started with something like R square, which itself is a linear vector space. I'm not telling you right now that it is a linear vector space. I'm trying to do something regarding with R square, and then you will be able to familiarize with the definition of the linear vector space. Okay, so scalar multiplication. You understand what is a scalar multiplication? You just need a x. You just need a real number. You just multiply it with some vector, and this is called as the scalar multiplication with respect to a vector. What do you get? Geometrically, you know that. Let's say this is your vector v. Initially, let's say this is your vector v. If I multiply it with alpha, which is greater than 1, so what will happen? This will become your, in the same line, this will become your alpha v vector. Let's say if you're multiplying with alpha which is greater than 1. If you multiply with alpha less than 1, then this will be your alpha v. And similarly, if you multiply with negative, it will go in the opposite direction. Let's say this is your v vector. So this is what we call as the scalar multiplication. This is what we call as the scalar multiplication. Okay. Now, what sort of properties and similar things? I mean, I can write it here. Why only r squared? If you think about r cube, R cube also, similar things can be done for the same. Similar things can be done for the same. I know for R cube also, I can define a addition like x1 comma y1 plus x2 comma y2 plus x3 comma y3, and obviously I can define this vector addition as x1 plus x2 plus x3 and then y1 plus y2 plus y3. This would be a vector addition. Okay, and similarly if I multiply a vector in 3 dimension, let's say this, then it will be multiplied with each of its tuples, each of its coordinates in the respective direction. So x3 j cap and then k cap, and then I can write this as alpha x1 comma alpha x2 comma alpha x3. So I can do a scalar multiplication in R cube also, that is any vector in R cube, that is it would be a space vector here. Usually it is defined by the term called as the space vectors are defined in the 3 dimensions and plane vectors in 2 dimensions. I hope it is clear till now. Now, just think about a little bit of things, things that I'm telling you right now. Okay. Again, just consider R square. Just consider R square. And I have already well defined two operations. One operations I have defined, which is called as a vector addition, and another well-defined operation is the scalar multiplication. These two are well-defined operations, isn't it? Now, if I tell you that what all things that you can think of into R square. So first of the things that you can think is that the vector addition is associative. Okay, the first thing that you can think of is closure. Let me write closure first. What do I mean by closure? See, by closure I mean that if I'm saying that my a1 comma a2 belongs to R square, and if I'm saying my b1 and b2 also belongs to R square, that is these two represents two plane vectors in R square, and if I add them up, where they are going to lie? Again they are going to lie in R square only, isn't it? So if I take two elements in R square, if I add them up, I'm going to get another element in R square only. So I say that my vector addition, so I would say my addition as an operation is closed. This is what I mean when I say closure. So closure holds, isn't it? The first thing is that closure will hold. The second thing that you can think of is that this particular vector addition would be associative. This particular vector addition would be associative, by which I mean that if I try to do this thing, a1 comma a2 plus b1 comma b2 plus c1 comma c2, or I do this way, a1 comma a2 plus b1 comma b2, this I do on one side and then add c1 comma c2. These are one and the same thing. So basically this would represent associativity. This is something that you can verify on your own, that this would be eventually equal to a1 plus b1 plus c1 comma a2 plus b2 plus c2, and same thing here. Similarly, one of another property that you can think of is commutative. That is, if you think that what vector addition could be commutative as well. So what do I mean? If I say that I have two vectors a1 comma a2 and b1 comma b2, whether I do this or I do this, this will yield me the same result, isn't it? So this is what you call as that your vector addition is commutative. Here what you say, here you say that your vector addition is associative. Okay, now you see another property that you can think of is existence of identity element. Existence of identity element, that is the origin. So if I take my let's say I have this a1 comma a2, and if I add a null vector to it, if I add a null vector to it, what I would get? I would simply get a1 comma a2. Or do I do this left operation? It will yield me the same result. So it implies that there exists an identity element, and this identity element is the null vector. Similarly, if you can think of identity element, then you can also think of something called as the inverse element. So if you have this a1 comma a2, corresponding to this you will have an inverse element, that is minus a1 comma minus a2. So if you add this thing, this is your inverse element, and if you add this inverse element to your original vector, you will get identity. So this is called as your inverse element. Now think about the properties that you can think of in scalar multiplication. Some of the properties that you can think about scalar multiplication. So the first property that you can think about or you can relate is, let us say I have two plane vectors. Let's say these are some u vector is given by, let's say, a1 comma a2, and you have another vector b vector which is given by b1 comma b2. Let's say these are two plane vectors. Now if I multiply my alpha with u vector plus v vector, isn't it that it will yield me this thing, alpha times u vector plus alpha times v vector? I mean, this is quite easy to verify. The second thing that I can think is that if I take this alpha plus beta times u vector, I will get this alpha u vector plus beta u vector. Okay, all these things are quite easy to think. That is the first property. I can say that my scalar multiplication distributes over the vector addition. Similarly, I can do this also. If I try to do this alpha times b u vector, I write this way, or I write alpha beta u vector. This is one and the same thing, isn't it? Let's say this is a v vector. You just take something like you just take these things, a1 plus a1 comma a2, b1 comma b2, and verify it your own self. I think this is something that you can verify on your own self. And the fourth property that you can think of is the existence of identity here as well. That is, if I multiply with 1, that is unit element, I'll get u vector only. And fifth one, if I multiply it with a 0 element, I will get a null vector. Okay, so all these properties in R square, you can think, right? So you can think of vector addition that I have stated. What is a vector addition that I have stated here? Here I geometrically represented it also in R square because it's easy to visualize things in R square here. You know that how vectors are added. After doing that, you know how a scalar multiplication can be executed. Also that you know that what all different properties you can think in case of vector addition. That is, closure is the first, the second is associativity, the third is commutativity, the fourth one is the existence of identity element, the fifth one is the existence of inverse element, and with regards to scalar multiplication, you can think of all these different properties. Once you know all these properties with regards to R square, you are in a position to think of something called as linear vector space. So till now, I hope everything is clear. Please let me know through comments that if anything you are not following or you're not able to follow. Motivation I have given you. Motivation I have given you. Is that clear? Okay. And each time you're going to get stuck, just go back to R square, think about R square, think about R cube, and try to correlate. For mathematics people, it remains to be an abstract concept. Okay. For physicists, in particular, you can think of R square, you can think of R cube, because there you have some physically realizable quantities. In general, I will define all these things for an n-dimensional space. Let's say I'm going to define Rn over R. Now for a physicist, n equals to 2 will suffice him to understand his physics on the plane space, that is on the Cartesian space. If a physicist take n equals to 3, he'll be able to visualize a three-dimensional space. But for mathematicians, limits are infinite. So he's going to talk about Rn over R. He's not going to stereotype it, but we are going to, because for us the most of the physical realizable quantities are in two-dimensional or three-dimensional space. However, when we'll enter into quantum mechanics, we are going to see functions and all sort of different things. So therefore, it is advisable that you should free yourself from R square and R cube. But if you are not able to, just keep in mind R square and R cube. Try to draw parallels anytime you get a confusion. So let us first start with the most basic definition, how actually it is started. And before starting it, one must understand what is field. Just a definition, I'm going to write it for you. What is a field? What is a field? So field is also a mathematical structure, and quite often in mathematics it is written. So therefore I'm going to write, because before starting vector space it would be good for you to have a little bit of understanding what is a field. Okay, so field is one where you have all these 9 properties that I'm going to write. So with respect to first plus and multiplication, these are the two binary operations. These are the two binary operations that we are going to consider before starting with the field. The first property should be the associativity with respect to addition, which indeed, let's say if I'm saying that an algebraic structure, if I say that an algebraic structure form a field, if I'm saying that an algebraic structure forms a field, what do I want to say? What do I mean then? Okay, so the first thing that I should mean is that if I'm defining a addition, then addition should be associative. Okay, and please don't confuse yourself with this addition with respect to don't confuse yourself with respect to the addition that you see in R. Okay, this is obviously for R, for real numbers you can have this kind of addition, but in general please don't place your head into this particular addition only. So basically you will see that your even complex numbers forms a field. So there you will have to define what do you mean by addition. Okay, so just I'm referring it to plus, so you can see that I'm referring it to addition. So first thing is, let's say if A is an element of a field and B is an element of field, and let's say C is an element of field, then A plus B plus C should be equal to what? It should be equal to A plus B plus C. The first thing that you should think is this. Second thing is the existence of an identity element. So if you have a null element such that you you can do this kind of operation, then this particular, and if let's say this 0 belongs to F, then we say that existence of identity is there. Since existence of identity we have talked, so for example, if A belongs to F, there should be an inverse element belonging to F such that A plus A inverse or A inverse plus A must give me back an identity, and certainly it is. Let's say I'm writing A inverse because for different other things you can have different other note, like for real numbers, if you want to think that if I have a real number 3, then minus 3 would be inverse for real number, I'm saying. The fourth property is associative commutativity. That is, if A belongs to F and B belongs to F, then A plus B is equal to B plus A. Then fifth property with regards to multiplication, that is A into B into C should be equal to A into B into C. The sixth property is the existence of identity here, that is A into E is equal to E into A is equal to A. The seventh property you can think of is the existence of inverse, that is for any A belongs to field except 0, that is 0 should not be there, because for multiplicative inverse you you ought to have something like this. So if you have a multiplicative inverse, let's say B, then A plus B or A into B or B into A should give you an identity. And why I'm taking out 0, let's say I want to find inverse of 0, so that would not be defined here, right? So basically, let's say if I'm saying X, then X into 1 by X would give me 1, that is unity element. So one has to remember that X cannot be 0, so therefore we exclude the possibility. The eighth property is the commutativity with respect to multiplication, and the ninth property is the distributivity, that is this multiplication operation distributes over addition. That is A plus B dot C should be equals to A dot C plus B dot C, or you can say A dot B plus C is equal to A dot B plus A dot C. So all these properties, if they are satisfied, we say that an algebraic structure is a field. What all common algebraic structures that we actually identify ourselves with? Real number systems. They form a field structure. Similarly, complex number systems, complex numbers, they also form a field. So having said all these things, having said what is a field, let us now try to define very formally what are called as the linear vector spaces. And don't worry, soon you are going to understand all these things, but try to familiarize all these things, because when we are going to study quantum mechanics, we are going to consider something called as the Hilbert space. So before defining Hilbert space, you must be in a position to understand a little bit about linear vector spaces. More you understand, more you familiarize yourself with these kind of things, more you'll be excelling well in your quantum mechanics. As I told you, linear vector space is a formalism in which your entire matrix mechanics has been written. So quantum mechanics can be divided into two parts. Quantum mechanics is divided into two parts. Okay, so Chinmay is asking some question. I'll answer your question. Okay, just give me a minute. Okay, just give me a minute. First, let us define the vector space. First, let us define the vector space. Okay, So I'll answer the Chinmay's question as well. But first, let us define the vector space. Cross product, no, yeah, that's not the. See, when I'm referring to field, for field, you'll have all these properties. You'll have all these properties. Okay, these are the properties that we are going to see for the field. I mean, this is an algebraic structure that I'm talking of right now. So, for example, whenever you talk of group, okay, so group is one of the algebraic structure. So when I say that, I'm saying that, let's say, uh, complex numbers form a group with respect to, let's say, addition, okay, or let's say real numbers form a group with respect to addition. There are certain properties which it is bound to follow. Similarly, when I say that an algebraic structure form a vector space, it is bound to follow certain properties. And similarly, when I say field, this is an algebraic structure, understand. So if I'm saying that there is a field, that there is a particular algebraic structure that forms a field, I would say the elements of that particular field would satisfy these properties. So in general, vector cross product and scalar triple product, I don't think these are the properties that are defined defined under the definitions of the field. No. So field is, this is what I'm writing right now. This is what are these are the properties that you should think while judging that whether an algebraic structure is a field or not. This is what I know. Is that clear till now? Okay, so now let us start with vector spaces. And from here, our learning would be more concrete. So we have already seen some of the things in R square, some of the things in R square. So similarly, the first property, let's say if I say a set V is forming a vector, is, let's say, is called a vector space over a field F, over a field F, if it has two operations. And what are those operations? So for example, whenever I started with R square, actually I referred two operations. The first operation was called as the vector addition. In general, I'll say here two operations. That is, first is addition, and second is multiplication of the vector elements with a scalar. Multiplication of elements of V by elements of, you can say, field, and this particular thing is denoted by a dot, that is multiplication. So for example, whenever I'm saying that algebraic structures form a vector space, I would refer that all these properties must be satisfied. The property number one should be that with respect to vector addition, it should have a closure. It should have a closure means if U belongs to V, if U belongs to vector V, if V belongs to, sorry, set V, so U is a vector which belongs to V, V is a vector which belongs to set V, then U plus V should also belongs to V. For all U and V belongs to V. So this is the first thing. That is with respect to the addition, or you would say that this particular addition should be a binary operation. It should be a binary operation. Binary operation means what? If I'm saying, let's say addition is said to be closed under addition. Addition is said to be closed under real number system. So what does it mean? Let's say I'm taking 2. 2 is a real number plus 3. 3 is a real number. It gives me 5. 5 is a real number. So if I'm saying that my operation is closed with respect to a set, what does it mean? It means, let's say, if A belongs to set S, B belongs to set S, then A star B should also belongs to set S. Then I would say that this particular operation, which is the binary operation, is closed with respect to uh, uh, is closed under, let's say, this set S. So if I'm saying that the first property with respect to vector space would be addition being closed. So if I'm saying that U belongs to V belongs to V, then U plus V should also belongs to V. Now you see there is another property that we did in R square also. Just keep in mind that R square. That if I'm saying there is a vector V, there is a vector U, sorry, there is a vector U and there is a vector V, and if I add it with W, then this particular addition is commutative. This particular addition is associative. If you can verify this for your algebraic structure, then yes, indeed, indeed this is the indication that associativity holds. The third property that I referred you there was the existence of a identity element. So the set V must have an identity element, must have an identity element with respect to addition. Okay, that is, there would exist a null element belongs to V such that 0 plus V is equals to V plus 0 is equal to V for all V belongs to V. Just remember all these things you've done in R square. So R square indeed forms a vector space. That is what we are going to see. The fourth property that we saw was existence of inverse. So every element of V has an inverse, with respect to this addition. That is, for every U belongs to V, there exists V belongs to V such that U plus V is equals to this identity here. This is identity, right? And we say that this V is an additive inverse of U. The fifth property was commutativity. That is, U plus V is equals to V plus U for all U and V belongs to V. Now with respect to multiplication, scalar multiplication. So what I told, scalar multiplication is what? It is the multiplication of the elements of field with the elements of V. The elements of V are called as vectors, and these elements of F are called as scalars. Understand this. Elements of V are called as vectors, and elements of these field are called as scalars. So if I take these elements from scalars and multiply it with vectors in V, we say that we are dealing with something called as the scalar multiplication, denoted by dot. So if I have this, first let us define an operation. So if I am defining alpha dot V, it is simply equals to alpha comma V, it is simply equals to alpha dot V. Let us define this operation, and the first thing that comes in mind, that if alpha belongs to field F and V belongs to V, then alpha V should belongs to V. That is, this particular scalar multiplication must be closed. The first thing is closed. That is, if V belongs to a set V and alpha is multiplied to it. So for example, I gave you this example that if I'm dealing with two-dimensional space, and let's say I'm doing a scalar multiplication, I'm going to get restricted to two-dimensional space itself. This is it. If I'm dealing with a vector, multiplying it with a scalar, so alpha times V vector is also restricted to the space R square. So indeed, scalar multiplication is a closed operation on R square. Is that clear? Okay. Now, what would be the seventh property? The seventh property, I told you that if I'm doing this alpha dot u plus v, it will give me alpha dot u plus alpha dot v. Understand this dot product, it is not dot product, this is scalar product. Right now, since I'm not referring them to as vectors, so don't get confused. Don't get confused. I have defined this alpha dot v, this is called as a scalar multiplication. Here I'm defining it as a scalar multiplication. If you're keeping in mind a vector, then you must be thinking that I'm defining a dot product. No, it's not dot product. This is scalar multiplication only. There you do not write dot. But right now I'm writing it in general, so that is why I'm writing dot here. So if I'm doing the same thing for r square, I would be saying alpha is a scalar, alpha times v vector is scalar multiplication. But here for the general cases, I'm writing dot here. The property number 8 would be if alpha and beta are two scalars, and if I scalar multiply it with some vector v, then this will give me alpha v plus beta v. The ninth property, I think this will be alpha beta v is equals to b. This is something. And the 10th property is the existence of unity element. If I take unity element 1 dot v dot 1 times v vector, it will give me simply v vector. So if all these properties are satisfied, we say that algebraic structure is the vector space. So let's say I talked about r square. I talked about r square. Now let us think of it. The vector addition is closed. Yes, indeed. Vector addition is associative. Yes, indeed. There exists an identity element. Yes. For every xy which belongs to r square, there is an element called as minus x minus y belongs to r square. Yes. So existence of inverse. Addition is commutative. Yes, indeed. X plus y, whether you write whether you write x1 plus y1 comma x2 plus y2, or you write y1 plus x1 uh, plus comma y2 plus x2, they mean one and the same thing. That is, if I add two vectors x1 x2 plus y1 y2, or I add y1 y2 plus x1 x2, these are same thing. So commutativity holds. Sixth, we know about scalar multiplication. If I'm saying that there is a vector v belongs to r square, then alpha times v vector should also belongs to r square. Closure. We also understand that if I'm doing this alpha v vector plus a w vector, I will be getting alpha v vector plus alpha w vector. Other property that I told you was alpha beta v vector. I can write it as alpha times beta v vector. It is very simple to see all these properties are verified. I have a unit element which gives me this thing, so not dot product, this would be 1 only. 1 into v vector would give me v vector. And another property I think I forgot, alpha plus beta distributivity would hold here as well. So addition distributes over scalar multiplication. So alpha v vector plus beta v vector. So all these properties, since they are satisfied, I can say that my r square forms a vector space over field what r. Here x and y are elements from real numbers. So I say that r square over r. Over r means what? Over field f. Okay, this is my field f. So r square over r forms a linear vector space. It forms a simply vector space. Is that clear? Similarly, we can define we can define an addition operation and a scalar multiplication over Rn. Similarly, we can define a scalar multiplication, a vector addition and a scalar multiplication over Rn. What is Rn? Rn is an n-dimensional space. So what is Rn? Rn would in general refer to this thing. Okay, and let us define two operations. First is called as a vector addition. So vector addition means if I'm doing this x1 comma x2 dash 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 xn, and I'm adding it to y1 comma y2 comma y3 dash 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 yn, this is equivalent to writing x1 plus y1 comma x2 plus y2 comma x3 plus y3. This is first, and secondly I'm defining a vector scalar multiplication. Sm I'm writing implies scalar multiplication as alpha times x1 comma x2 xn, it is equals to alpha x1 alpha x2 alpha xn. So it is quite easy to see that these two are the well defined operations, and in accordance to these two operations, I can say that Rn over R forms a vector space. So I can say that Rn forms a vector space over R. Is that clear, or should I verify the properties for you? Please let me know. Okay, let me do it for you once. So it is quite easy to see. It's quite easy to see that addition is associative. Addition is what you can say. It is commutative in R. So indeed in Rn also it will remain the same. This is something that you can do on your own, so I'm not doing it. Also, addition is commutative. Addition is associative and commutative. Now regards remaining properties, the identity element in Rn would be, and this would be identity element. What would be an inverse element? Let's say if I have a vector x, or you can say x, which is given by x1 comma x2 dash 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 xn, corresponding to it there would be an inverse element minus x1 minus x2 dash 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 minus of xn. All these for this particular element there is an existence of an inverse element. Why it is called an inverse element? If I add this particular element to this, I will get an identity. Okay, and similarly, if you have alpha belongs to R, if you have beta belongs to R, then clearly alpha plus beta times x, that is x1 comma x2 dash 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 xn, you will simply get it as alpha plus beta times x1 plus alpha plus beta times x2 plus alpha plus beta times comma alpha plus beta times xn. Okay, and if you just think, if you can just distribute it inside, you will get alpha x1 plus beta x1 then comma alpha x2 plus beta x2 dash 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 alpha xn plus beta xn, and then you can write it as alpha x1 comma alpha x2 dash 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 alpha xn plus beta x1 comma beta x2 dash dash beta xn, and similarly you can write it as alpha x1 comma x2 dash 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 xn plus beta x1 comma x2 dash 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 xn. So clearly you can see that your um, you can see that your scalar multiplication is distributed. Here it is. Okay, and similarly all the other properties can be verified. All the other properties can also be verified. Okay, so all the other properties can also be verified. Is that clear, or should I do all these properties? I mean, this is something that you can do on your own also. If that is the case, let us move a little bit further. What do you think about this set? Okay, so what do you think about the set of complex numbers? So I'm defining set of complex numbers. Set of complex numbers, and it also forms a real vector space. Is also form a real vector space. What do I mean by real vector space? That is vector space over field R. Whenever I say what is a real vector space, it implies I'm stating that it is a vector space over R. And indeed it is. See, whenever you talk of complex numbers are nothing but their ordered pair of real numbers. So eventually, since you know that R square over R forms a vector space, R square forms a vector space over R. So therefore, clearly, complex numbers also form a real vector space. Is that clear? Because after all, what all things that needs to be seen? The first thing that needs to be seen is what did I tell you? That addition of a complex number will give you a complex number. Let's say if I'm saying there is a complex number, let's say uh, a1 comma b1. Let's say this is your complex number, which implies what I'm writing a1 plus iota b1. Okay, and another complex number, let's say a2 comma b2, which is a2 plus iota b2. If I add them up, what I'm going to get? I'm going to get a1 plus a2 comma b1 plus b2. Okay, so this also is a complex number. This is also a complex number, isn't it? So addition is committed. Addition is closed, and then you have this additive. So basically, what you can do? You can associate your complex number with R square, and since we know that R square forms a vector space over R, so therefore complex numbers, the set of complex number also forms a vector space over R. So therefore we can say that set of complex numbers form a real vector space. If you want, I can do the properties for you, just for the confirmation. So if I say that a1 comma b1 uh, plus a2 comma b2, if I want to do, and if I add another a3 comma b3, this would be some same thing as writing a1 comma a2, sorry, a1 comma b2, a1 comma b1 plus a2 comma b2 added first, and then added with a3 comma b3. So associativity holds. Existence of 0 is there indeed. So you know that a complex number, any complex number, can be represented on two-dimensional space. That is, you just need a Cartesian plane to represent set of complex numbers. So indeed this 0, that is 0 comma 0, exists in C, such that if I have a complex number a comma b, if I add this 0 comma 0, I will get a comma b. So existence of identity, existence of inverse. For every a comma b you have minus a minus b. Okay, for every a comma b you have minus a comma minus b. This is called as inverse. So if a comma b is a complex number, minus a comma minus b is also a complex number. Okay, so all these properties are verified, and similarly you can verify the other properties with respect to uh, scalar multiplication also. So if I have this alpha as a scalar number, a real number, and if I'm multiplying, let's say a plus iota b, let me write it this way. So it will give me alpha a plus alpha iota b. What does it imply? It implies alpha a comma alpha b, or I can write it as equals to alpha a comma b. So if I'm doing alpha a comma b, I'm getting alpha a comma alpha b. So this is scalar multiplication is closed because alpha a is also real, alpha b is also real. This entire thing I can write it in this way. So this is a complex number, isn't it? This is a complex number, alpha a plus alpha iota alpha b. This is a complex number, isn't it? So scalar multiplication is well defined. It is closed. That is, even if there is an element from complex numbers, that is a plus iota b, if I multiply it with alpha, this particular thing will again remain in complex only. So it is closed. You can verify on your own that alpha dot some vector, let's say if I'm taking a1 plus iota b1 plus a2 plus iota b2, I'm going to get what? I'm going to get this as alpha times a1 plus a2 plus iota b1 plus b2. This is what I'm going to get, isn't it? Or you can write it in this fashion: alpha times a1 plus iota alpha times iota b1 plus alpha times a2 plus iota times alpha b2. It is similar to writing alpha times this particular, let's say I'm writing it as u1, and this particular thing I'm writing as u2. So alpha dot u1 plus u2 is equal to alpha dot u1 plus alpha dot u2. Okay, and similarly other things can follow. Other things I'm leaving up to you. You can do it on your own. So always remember that the set of complex numbers form a linear vector space, forms a real vector space. Forms a real vector space. Now, what do you think about this particular set? Set of all polynomials in X with real coefficients. That is, I'm talking of set of polynomials, let's say P, which is written as summation I equals to 0 to n ai x raised to power I, where n belongs to natural and ai belongs to R. So what does it represent? It represents a set of polynomial, isn't it? So if I take all different AIs and if I take all different powers, then I can make all sort of different polynomials, isn't it? Is that clear? Are you able to identify with this particular statement? Okay, is that clear or not? Please let me know. So isn't it, this will form let's say you take all different AIs. Okay, you take let's say if I'm saying that let us take that a naught is equal to 1, let's say a1 is equal to 1, let's say a2 is equal to 1, and then all others are 0. So what polynomial it represent? It would represent 1 plus x square, isn't it? So this is one polynomial, isn't it? Similarly, you can make all other polynomials till degree n. Let us say I'm saying that let's say ai is equal to 0 for all I lying from 0 to n minus 1, and n is equal to 1. So what does it represent? It represents a polynomial of degree. It represents x raised to power n. Yes. So obviously this particular structure would refer to us, can be referred to as the set of all polynomials in R. And since a1, a2, a3, n's are all real numbers, so this is a polynomial with, this represents a set of polynomials in X with real coefficients. Okay, does it form a real vector space? Does it form a real vector space? Indeed it does. See how. The first thing that you should think is addition of two polynomials. Let's say I'm just taking polynomials right now for example. Addition of polynomials is associative as well as commutative. In fact, it is closed also. Why? You take two polynomials. Let's say take x square plus 1 and let's say I'm adding it with x plus x cube. Okay. So this is one polynomial, this is one polynomial. If I add them up, what I'm going to get? I'm going to get x square plus x plus 1, which is another polynomial. So this belongs to P, this belongs to P, and this also belongs to P. Okay. So addition is addition of polynomial is again a polynomial. So you can say addition of polynomial is again polynomial. So addition is closed. Okay. Now if you think commutativity, yes indeed commutativity exists. For example, x square plus 1, if I want to add it with x cube plus x, or I add x cube plus x and then I add x square plus 1, indeed it will give me the same result, because I know that addition is commutative as well as associative in R. So therefore you can say that your addition of polynomial will be an associative operation as well as commutative operation. Is that clear? So both commutativity and associativity holds in addition of polynomials. We also understand that trivially 0 is a polynomial. Trivially 0 is also polynomial. See, if I take all these ai's as 0, then 0 is also polynomial, and this would be an identity for that matter. And for a polynomial that is a naught plus a1x an x raised to power n, there always exists an inverse, that is minus a naught minus a1x minus a2x square dash dash minus an x raised to power n. This always exists. So for a polynomial of order degree n, there always exists another polynomial which is inverse. So this is existence of inverse. Further, with regards to other things with regards to scalar multiplication, it's quite easy to see that if I take a scalar, let's say 3, and if I multiply it with a polynomial, so clearly you can see that this would be 3x square plus 12. Similarly, if I have 3 into 4 into x square plus 4, I can write it as 3 into 4x square plus 16, which is equals to 12x square plus 48, which is equivalent to writing 12 into x square plus 4. There exists an unity which gives me x square plus 4 is equal to x square plus 4. So I have taken an example and made you understand all these things. You can generalize it as well. So with regards to scalar multiplication also, all the requisite properties for vector spaces will be satisfied. So therefore we can say that set of polynomials forms a real vector space. In fact, another thing, bigger generalization would be if, let us consider a set S. Let us consider a set S of all functions from R to R. So we are considering all the functions from R to R. And we define something called as addition of functions. So addition of function f plus g is simply adding the two functions independently. That is, f plus g is given by fx plus gx, and this is called as the pointwise addition of function. And let us say, let me take some alpha belongs to R, then, and let's say some f belongs to set S, which is the set of all functions, then alpha times f, which is defined as alpha dot f of x. This is how you define the scalar multiplication of function fx. One can clearly see that this particular set S also forms a real vector space. In fact, further generalization can also be seen. Further specification can be seen that set of all continuous functions, set of all continuous functions over R forms a real vector space. Forms a real vector space. So since all the continuous functions forms a real vector space, so clearly one can say that set of polynomials being continuous function should form a real vector space. So all these things I'm leaving it for you to understand and deal with, because all these things would require you only to verify all the 10 properties that I mentioned initially. If you can verify all those 10 properties for each of these set, if you want to do it as a homework, you can do it. Now let us try to do one example, and that example will be very effective in order to define what is called as the what is called as the subspaces. Okay, so let us define that. Let us do that, and then let us define what is called as subspaces. So let me define a set. I mean, is that boring? Please let me know. I know this is slightly boring, but okay. So let us consider this set. Let V be a subset of R square given by x comma y, where y is related to x by y is equal to 5x. And we define the vector addition the same way we defined in the R square. So this is how we have defined the vector addition and the scalar multiplication. And please remember, this is here y is specifically related to x by this particular equation. That is, this is a linear equation here. Okay. Now think about this. The question is, does it form a real vector space? Does it form a real vector space? So I'm coming to now, since I've done a few questions, now I'm going to do with one by one. The first thing that needs to be seen is binary, that is closure, whether closure holds or not. So I know that if x1 comma y1 belongs to V and x2 comma y2 also belongs to V, then it implies that y1 would be 5x1 and y2 would be 5x2. And if I add y1 plus y2, it would be equals to what? It would be equals to 5 times x1 plus x2. Right? So y1 plus y2 would be 5 times x1 plus x2, isn't it? So, and if I add them up, what I'll get? x1 comma y1 plus x2, sorry, x2 comma y2. If I add them up, I will get x1 plus x2 comma y1 plus y2, isn't it? Now remember, this is your x and this is your y. This is your simply x and this is simply y. Clearly, y is equal to 5x, isn't it? Because now your y is what? Now your y is y1 plus y2. And I have written it here that y1 plus y2 is what? It is equals to 5 times x1 plus x2. So here is your x, here is your y. So y is related to x by y is equal to 5x. Also that also x1 plus x2 comma y1 plus y2. So I know that if x1 comma y1 belongs to V, x2 comma y2 belongs to V, clearly their sum also belongs to V. In order that their sum should belongs to V, y must be related to x by y is equal to 5x, which you can see here. Is that clear? Please let me know. Is that clear? Please let me know. The second thing that you should think of is associativity. So let us say I'm saying x1 comma y1, where y1 is equal to, please remember, it is equal to 5 times x1 plus x2 comma y2 plus x3 comma y3. Whether I do this or whether I do this, I'm going to get the same result. I think this is quite easy to verify, so I'm not going to verify it for you. This is quite easy to verify that these two things are equal. So associativity holds. In fact, you can clearly verify yourself that commutativity also holds. So all these two things I'm leaving up to you. Commutativity also holds over vector addition. Now, clearly 0 comma 0 also belongs to V, isn't it? So if your x is 0, then your y is equal to 5 times 0 is equal to 0. So clearly x comma y such that y is equal to fx, y is equal to 5x. If I take x equal to 0, I'll get y equal to 0. So clearly in this space only you will have 0 comma 0. So 0 comma 0 belongs to this space, isn't it? So there is existence of identity element. Why? Because if I add x comma y plus 0 comma 0, I will simply get x comma y. And please remember here y is equal to 5x. So if you want to write it in this fashion, x comma 5x plus 0 comma 0, what you will get? You will simply get x comma 5x only. Okay, or you add 0 comma 0 to x comma 5x, again you will get what? You will get x comma 5x. So clearly 0 comma 0 serves as an identity element here. Don't you think that if x comma y belongs to V, then minus x comma minus y also belongs to V? See how? If x belongs to V, then y is equal to 5x. This also belongs to V. And if I'm saying minus x belongs to V, then y is equal to 5 into minus x, which is equals to minus 5x, also belongs to V. And if I take an so minus 5x also belongs to V. So if there is a x comma 5x, corresponding to this you have minus x comma minus 5x, which when added gives you an identity back. So therefore there is an existence of inverse element. There is an existence of inverse element. Similarly, if you want to clarify this, let's say alpha x comma y will give you alpha x comma alpha y. Then you can verify on your own self that alpha plus beta x is equals to alpha x plus beta y, beta x, and all other scalar multiplication property can be verified. Okay, so this implies that my V, I think this is something easy to see now. I think this is something that you can do on your own, so therefore I'm not bothering much. Okay, okay, my mistake. This is something I'm leaving it to you. So you can clearly see that this V forms a real vector space. Now don't you think that what does y is equal to 5x represent? What does y is equal to 5x represent? So clearly if you see that what is y is equal to 5x? Y is equal to 5x represents the represents a straight line. It represents a straight line. It represents a straight line which indeed is a subset of R square. If you consider it as a subset of R square, if you think, isn't it a subset of R square? What is R square? R square would represent all the points in the Cartesian plane. And what does y is equal to 5x represent? Y equal to 5x categorically would represent all the points in R square that are lying on this particular line. That is y is equal to 5x. Don't you think that this y is equal to 5x, all these points are, you can say that y is equal to 5x is a subset of R square. Yes or no? Should I repeat it again? Yes or no? Don't you think that this particular set, that is V, which was given by x comma y, where y is related to x by 5x, is a subset of R square? Okay, and indeed what does it do? It goes on to make a vector space itself. It goes on to make a vector space itself. Such a space V is referred to as a subspace. Such a space V is referred to as a subspace. So basically, a subspace is a vector space in its own right. Okay. Further, let's say if R square is a vector space, a subset of it forms a vector space, that is, it qualifies all the properties that are required for a vector space, then that particular subset is termed as a subspace. Is that clear? Is that clear or not clear? Please let me know. Now question arises that is that always we are going to do this way, that we are going to take, we should know that the main set is a vector space, and then we'll think of it, think of a subset, and then we'll execute all these properties. Okay. 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 So there is a different way also. There's a different way, and that different way I can say that there are tests in order to find whether a space is a subspace or not. So if you know that there is a subspace W of a vector space V, what are those conditions required to claim that W is a subspace of V? For that, I'm writing a few results. Result number 1 is a non-empty subset. The first thing that you should see that whether that set W is a non-empty or not. If it is an empty subset, then okay, then it's not then that it does not qualify the statement. So basically, a non-empty subset W of a vector space V over a field F is a subspace of V if and only if the first is that if W1 belongs to W, W2 belongs to W, then it should imply that W1 plus W2 belongs to W. Second, okay, so we were doing a question where we were doing actually we were saying that W is equals to x comma 2x comma 3x, and where x belongs to R. So basically what sort of elements would it represent? Just think of it. So it will be like 1 comma 2 comma 6, right? If I'm writing 1 now, so 1 comma 2 comma 3. If I'm writing 2 comma 4 comma 6, and such elements will be there. So clearly these are elements in R cube, right? So these are elements in R cube, yes or no? So these are elements in R cube only. Now if you think about 0 comma 0 comma 0, so if you take x is equal to 0, what are you going to get? You're going to get 0 comma 0 comma 0, right? And 0 comma 0 comma 0 would indeed belongs to W. If it belongs to W, then does it not say that your W is a non-empty subset? Because 0 comma 0 comma 0 is there in W. So clearly W would be a non-empty set. W would be a non-empty set. Yes or no? Please let me know if there is an issue. Okay. Okay, just give me a minute, I guess. There is a problem. Okay, just give me a minute, I think. Okay. Uh, am I audible now? So, okay. So, W would indeed be a non-empty set. W indeed would be a non-empty set. Right? Yes or no? Am I audible, right? Okay, so W would be indeed a non-empty set. I guess there are no responses, so I'll move further. So if so, W would be a non-empty set, right? If W is a non-empty set, let us move further. Now, if W1 belongs to W and W2 belongs to W, if W1 belongs to W and W2 belongs to W, let us say, what does it mean? Let's say I have W1 as x comma 2x comma 3x, and I have W2 equals to y comma 2y comma 3y. Now, if I do alpha times W1, I will get alpha times x comma 2 alpha times x comma 3 alpha times x, and then I have this beta times W2. What I will get? I will get beta times y plus 2 beta times y plus 3 beta times y, right? And if I add them up, what I'm going to get? Alpha W1 plus beta W2 is equals to alpha x plus beta y comma 2 alpha x plus 2 beta y comma 3 alpha x plus 3 beta y. What it is equal to? It will be equals to writing alpha x plus beta y comma 2 times alpha x plus beta y comma 3 times alpha x plus beta y. And alpha x plus beta y, let that be z. Let that be z. So is it not equal to writing z comma 2z comma 3z? So clearly this belongs to W. So if your W1 belongs to W, your W2 belongs to W, and alpha W1 plus beta W2 also belongs to W, where W is a subset of R cube and R cube forms a vector space. So clearly I can say that W is a subspace of R cube. Is that clear till now? Please let me know. See, I understand all these things are quite, you can say that you cannot relate them as such when it comes to physics. But do understand that the way the pattern is being changing in the net exam, you can expect such questions. Recently in 2019, they've asked a question on vector space. So if you are well versed with all these things, I hope you will be doing good in your exam. And once that you are sound at all these things now, So you'll be doing good in quantum mechanics, don't worry. It would hardly take us this week at least to understand all these kind of nuances of linear vector spaces. I hope it is clear. I'll wait for a minute for responses and then I'll move ahead. Now let us think of another example that will make things clear for you. And that is, let's say I'm taking a bigger example. Now tell me which of the following subsets W of R. So which of the following subsets W of R raised to power 4 are subspaces of R raised to power 4. R power 4 means it is 4-dimensional space. Okay. So the question is, what do you in for what of the for which of the following cases do you think that there would be a subspace? Okay, so let's say if I'm saying that I'm considering a set W given by x1 comma x2 comma x3 comma x4 such that the first element, that is x1, if I'm keeping it as 0, will it form a subspace of R raised to power 4? And please remember, we have already proven that Rn is a vector space over R. This is something that we've already proven, that Rn is a vector space over R. Since we know that Rn is a vector space over R, so clearly we can say that R is power 4. So this 4-dimensional space is also vector space. And indeed, if I'm keeping one tuple 0, that is one of the coordinate as 0, indeed this forms a subset of R raised to power 4. Okay, so let us do it. Clearly, one thing is very much clear, that if I consider the 0 comma 0 comma 0 comma 0, it indeed belongs to W, where W is equal to what? W is equal to 0 comma x1 comma x2 comma x3, right? Because all one needs to have for the option number A is that the first tuple should be 0. If first tuple is 0, and then keep all these elements anything, so you have element 0 comma 0 comma 0 which belongs to W, which implies that W is a non-empty subset. Isn't it? This is something that you should see. Indeed, it is a non-empty subset because 0 comma 0 comma 0 belongs to W, right? Because 0 comma 0 comma 0 comma like this qualifies that your first coordinate is 0. All other coordinates can be anything, so obviously you have placed them as 0. So is it not that this does belong to W, right? Because here the first coordinate is 0. So this does belong to this. So what are we talking? So for A, we are talking about this kind of space. In A, we are talking of this kind of space. So this is the set A. Clearly, since 0 comma 0 comma 0 belongs to W, 0 comma 0 comma 0 comma 0 belongs to W, so W is a non-empty set, non-empty subset. Is it fine? Okay, good. So W is a non-empty subset. Now let us try to find the other two properties. So let's say if I'm talking of W1, which is equal to 0 comma, let's say x2, x3 and x4, and there is another W2 which is, let's say, 0 comma y2 comma y3 comma y4. Okay, and let us say I'm talking of alpha W1, which will be 0 comma alpha x2 alpha x3 comma alpha x4, and you have this beta w2 which is equal to 0 comma beta x2 beta y2 comma beta y3 comma beta y4. Then indeed it will give me alpha w1 plus beta w2 will give me what? It will give me 0 comma alpha plus beta, sorry, alpha x2 plus beta y2 comma alpha x3 plus beta y3, and then alpha x raised to power 4 plus beta y raised to power 4. Indeed, you can see that alpha is a real number, x1 is a real number, their multiplication would be a real number, beta is a real number, y2 is a real number, their multiplication would be a real number. So this you can correspond to 0 comma some z2 z3 z4. Indeed, this particular structure corresponds to W. So your alpha W1 plus beta W2 also belongs to W. Implies what? It implies that this particular subspace of R power 4, this particular subset of R power 4 is a subspace. Is a subspace. Now, what do you think about option number 2? Does it form a subspace? Let us see. So, option number 2 suggested me that keep the tuple x2 as 1. So, first let us write what is that kind of space. So, we are talking of a space W, or we are talking of a subset W of R power 4, which is defined in this manner: x1, comma 1, comma x3, comma x4, where x1, x3 and x4 belongs to R. Okay, so we are talking of this. We are talking of this particular subset of R power 4. Now clearly one can see that W is a non-empty subset. Clearly why? Because you know that you have this 1, comma 1, comma 1, comma 1 belongs to W, isn't it? Clearly, only condition that needs to be satisfied is that whether x2 is 1 or not. Yes, indeed. And all other things can belong to R. Yes, indeed, this particular thing belongs to W. So we can say that W is a non-empty subset. It is a non-empty subset. Okay, now if W1 belongs to W, what it would be? It would be in this fashion: x1, comma 1, comma x3, comma x4. And if W2 belongs to W, let us say it is equals to y1, comma 1, comma y3, comma y4. Even if I add them up, let's say alpha is equal to 1 and beta is equal to 1, what I will get? I will get W1 plus W2. It would be equals to what? It would be equals to x1 plus y1. Fine. It would be 1 plus 1, which is 2. Here it would be x3 plus x4, x3 plus y3, and here you will get x4 plus y4. These are all real numbers. You can write them as z1. This will remain 2. You can write it as z3. it will remain Z4. Does it? It does not belongs to W. See, it does not belong to W. In order to qualify to be in W, your second coordinate, that is x2, must be 1. Here it is. X2 is 2. So clearly, this is not a subspace. For simplicity, I have taken alpha is equal to 1 and beta equal to 1 so that you can relate very quickly. Is that clear? So this is not a subspace. I hope it is clear. So we'll do till subspace today. Tomorrow we'll do bases and dimensions and all those things that are really important for us. Okay, and from tomorrow also we'll start with quantum mechanics slightly. Okay, so don't worry. Is that clear? So this is not a subspace. Why it is not a subspace? Because I have done W1 plus W2, taken alpha and beta is equal to 1, because alpha and beta can belong to real R. So why not take alpha is equal to 1 and beta equals to 1? If I take them up, I would find that this particular thing does not belongs to W. What particular thing? Alpha W1 plus beta W2 does not belong to W. Clearly it negates the condition for being a subspace. So therefore, this particular W, which is given by x1, 1, x3, x4, does not form a subspace of R power 4. Is that clear? If you remember, I had written another theorem. So there were two theorems that I mentioned. One theorem which I'm currently using right now is this. Another theorem was, if alpha belongs to field F and W belongs to W, then alpha W should belongs to W. If I'm saying that W is a vector space over V, then alpha belongs to field F and W belongs to W, then alpha W should belongs to W. So let us see whether this is also violated or not. So see, take alpha is equal to 0 and my W is equal to what? My W is equal to x1, 1, x3, x4. If I do a scalar multiplication 0 times W, it will give me 0, x1, 0 into 1, 0 into x3, 0 into x4. This would be 0, 0, 0, 0. Clearly does not belongs to W. So here, from here also we can say that W is not a subspace. Is that clear? So from both of the sides. Okay, now there is a question number, option number 3rd, which suggested us that x3 should be less than 0, right? This is what it was suggested. So we are defining a subset which is x1, x2, x3, x4, such that x3 is negative, and we want to see that whether this particular W forms a subspace of R power 4 or not. How to go about it? Just think that one of the element can be this 0, 0, minus 1, 0. Indeed it can be. So clearly we can say that W is not an empty set. Clearly it is a non-empty set, right? And now I know that this W belongs to W1. Let's say it is W1 belongs to W, and let's say alpha, let us take it as minus 1. So minus 1 scalar multiplication W will give you 0, 0, 1 and 0. Clearly it does not belong to W. So clearly if W is a subset of V, then if W is a subset of V, then alpha times W must belongs to W. Alpha times W must belongs to W, and W1 plus W2 where W1 and W2 are both belonging to W should also belong to W. If this is the case, only then we can say that my W is forming a subspace. But if I take alpha from a field which is real number, let's say -1, and if I multiply, scalar multiply it with W, what am I getting? I'm getting 0, 0, 1, 0. And clearly x3 is positive, which should not be the case. For in order to qualify for W, your x3 should be negative. So clearly this is not a subspace. So this is not a subspace of R power 4. Is that clear? Okay, now let us do a few more questions so that this particular thing gets into your understanding, and then I'll define something called as a linear computation. I hope you're finding some sort of interest. Okay. Now let us think of this. If 2x1 plus 5x4 is equal to 0. This was option number D, right? This was option number D. Okay, so this was option number D. So clearly, we are talking of a space, we are talking of a subset x1 comma x2 comma x3 comma x4 such that xi can belong to real number R, but there is a provision that you need to keep in mind, which is that the 2x1 plus 5x4 must be 0. If I take all these terms as 0, x1 as 0, x2 as 0, x3 as 0, and x4 as 0, does it not qualify our definition that 2 times 0 plus 5 times 0 is equal to 0? Yes, indeed, it qualifies this particular statement. So clearly I can say that 0, 0, 0, 0 would belong to this W. So I can claim first that this is a non-empty subset. So this is a non-empty subset of R power 4. This is one thing that you should keep in mind. Another thing that seems that needs to be seen here is that let us apply the first theorem. The first theorem said that if W is a subset of V, then W forms a subspace over V, subspace of V, if and only if W1 belongs to W, W2 belongs to W, then W1 plus W2 should belong to W, and if alpha belongs to some field F, then alpha times W should belongs to W. Okay, so this is our first theorem. Okay, let us try to apply that and let us see things work out. So see, we can do it using the other theorem also, but let us first apply theorem 1 so that you should be able to understand both of them. So if alpha 1 is what? So let's say alpha 1 is, let's say it is x1, comma x2, comma x3, comma x4, such that, please remember, 2x1 plus 5x4 is equal to 0. Similarly, if I define W2, W2 will be equals to what? W2 will be equals to y1, comma y2, comma y3, comma y4, such that 2y1 plus 5y4 is equal to 0. Okay, these two are the conditions given to you. Now let us try to find what is W1 plus W2. So your W1 plus W2 would be simply x1 plus x2, comma x1 plus y1, sorry, x2 plus y2, x3 plus y3, and then you have this x4 plus y4, isn't it? Now think about all these things. So this is some z1, here it is some z2, here it is z3, and here it is z4. Do you think that 2 times z1 plus 5 times z4 is equal to 0? Let us see. So what is 2 times z1? 2 times z1 is simply 2 times x1 plus y1. And what is 5 times z4? It is simply 5 times x4 plus y4. So clearly I can write it as 2 times x1 plus 5 times y, x1 plus 5 times x4 plus 2 times y1 plus 5 times y4. It is also equal to 0. It is also equal to 0. Therefore, it implies 2z1 plus 5z4 is equal to 0. It implies what? It implies that it belongs to W. So W1 if it belongs to W, if W2 it belongs to W, what is the condition? That if W1 belongs to W, that it implies that x1, x2, x3, x4, which is W1, must be in such a way that 2x1 plus 5x4 should be 0. W2 if it belongs to W, it implies y1, y2 plus y3 plus y4 be in such a way that 2y1 plus 5y4 must be 0. If I've added them up, let's say it is equals to x1 plus y1, x2 plus y2 plus x3 plus y3, x4 plus y4. Let us write them up as z1, z2, z3, z4. I have proven that 2z1 plus 5z4 comes out to be 0. Then it implies that w1 plus w2 also belongs to W. The condition for remaining in W was that whatsoever be your 4 of these tuples, that is x1, x2, x3 and x4, the condition is required is that the 2 times the first element plus 5 times the last element should give you a 0, and then indeed here you can see is the case. If you want to see that if alpha belongs to R, any alpha belongs to R, and let us take W. Let's say W belongs to W, and which is equals to, let's say, x comma x1 comma x2 comma x3 comma x4. So clearly if I multiply alpha with W, what I'm going to get? I'm going to get alpha x1, alpha x2, alpha x3, and this is alpha x4. Clearly all these are real numbers. Clearly all these are real numbers. We name them as z1 comma z2 comma z3 comma z4. Okay, and just see whether your whether 2z1 plus 5z4 gives you a 0. Indeed it gives us, because this is 2 times alpha x1 plus 5 times alpha x4. Take alpha common, you will get 2x1 plus 5x4. Indeed this is 0. Okay, this is 0 here. So if an element belongs to W, then 2x1 plus 5x4 should be 0. So here it is also alpha into 0 is 0. So clearly this alpha W also belongs to W. So it qualifies the statement 1. So therefore we can say that this is a vector space. This is a vector subspace. This is a subspace of R power 4. The same way we can do the definition 2 also. I'm leaving it to you. That is also quite easy to see, that if you take, let me do it. Let alpha and beta belongs to R. Let alpha and beta belongs to R. And let us say x1 comma x2 comma x3 comma x4. Let us say this is your w1, and let's say your w2 is y1 comma y2 comma y3 comma y4. And to remain in y1 x1 w1, you should have 2x1 plus 5x power 4 equal to 0. And to remain in w2, your 2y1 plus 5y4 must be equal to 0. Now if you take alpha times x1 comma x2 comma x3 comma x4 plus beta times y1 plus y1 comma y2 comma y3 comma y4, what are you getting? You're getting alpha times x1 plus beta times y1 comma alpha times x2 plus beta times y2 plus alpha times x3 plus beta times y3 and comma alpha times x4 plus beta times y4. Now if you just think what would be a 2 alpha x1 plus beta y1 plus 5 times alpha x4 plus beta y4, it would be simply equals to writing 2 times, if you take alpha common out, you will get 2x1 plus 5x4, and if you take beta common out here, you will get 2y1 plus 5y power y4. This is 0, this is 0, so you are getting 0. So clearly I can say that if w1 belongs to W, w2 belongs to W, then alpha w1 plus beta W2 also belongs to W implies my W is a subspace of R power 4. Is that clear? Now always remember there is a notation that I'm giving it to you. So let's say I'm talking of let V be a vector space over F. V be a vector space over F. Okay, and small v be any element in V. Then the subset alpha times V, where alpha belongs to field F, is a subspace of V. Is a subspace of V. So I'm leaving it to you, and this particular subset is at times written this way. So don't get confused. This way. Okay, so it's quite easy to see that if V is any element in V, then alpha times V will be element in V, beta times V will be element in V. So alpha plus beta V must be belonging to V. So that is alpha V plus beta V would also belongs to V. Okay, and also you can see that if okay, also you can see that what was the remaining case, alpha. Okay, so clearly we can see that so this is your W1, this is your W2, this also belongs to V. So always remember that that this particular subset, that is alpha V. Okay, this was the case, right? So alpha V, it always forms a subspace of V. So let us say I took a vector space which was R square, if you remember, and a subspace I considered, that is y is equal to 5x. Y is equal to 5x. So this particular subspace will always form a vector space. This will always be a subspace. This is what I want to say. Is that clear or not clear? Or let me. Should I explain you more? Just let me explain you by example or something. Otherwise, you will not be able to get what I want to say. Let me take an example. That would be good for you. I think this would be a little bit difficult for you. See, what I want to convey is that if, just understand, if you're not able to see, what I want to convey is, let us say that if V is a vector space over F, and let V belongs to any, let's say V belongs to vector space V or set V, V belongs to set V, and if I multiply this with some scalar, that is alpha, then alpha times V, this would be a subset of V. This will also form a subspace of V. This will also form a subspace of V. So let's say V was a vector space. Now if you define another set which is alpha times V, this would be a subspace of this vector space. This is what this theorem suggests. Okay. Okay, now just take a few examples and then let us conclude our class. So just think about a few of the subsets and prove that these are subspaces or not. So let us say this is your W1, which is x1, x2, x3 belongs to R cube, such that 2x1 plus x2 minus x3 is equal to 0. Does it form a subspace? of R cube? Does it form a subspace of R cube? Does it form a subspace of R cube? So let me help you. Okay. So if again let us verify it. So let alpha belongs to R and beta belongs to R. Let alpha belongs to R and beta belongs to R. Now let us take some x1 comma x2 comma x3. It belongs to uh, let us say this is your w1, where remember 2x1 plus x2 minus x3 is equal to 0. And let us take another one, y1 comma y2 comma y3. Let us say it is equal to w2, and say 2y1 plus y2 minus y3 is equal to 0. Is that clear? Now alpha w1, which is alpha x1 comma alpha x2 comma alpha x3 plus beta y1 comma beta y2 comma beta y3 equals to what? It will be equals to writing alpha x1 plus beta y1 comma alpha x2 plus beta y2 comma alpha x3 plus beta y3, right? And we know these are the conditions that is going to satisfy it. Now let us see whether these are satisfied here. Let's say this is your z1, this is your z2, and this is your z3. If 2z1 plus z2 minus z3 is equal to 0, only then we can say that this belongs to W, right? So let us calculate what is 2z1 plus z2 minus z3. So it is equals to 2 times alpha x1 plus 2 times beta y1 plus alpha x2 plus beta y2 minus alpha x3 minus beta y3, right? If you take alpha common out, what you are going to get? You are getting 2x1 plus x2 minus x3 plus beta times 2y1 plus y2 minus y3. This is equal to 0. This is equal to 0. That implies 2z1 plus z2 minus z3 is equal to 0. That implies this belongs to W. It implies if W1 belongs to W, W2 belongs to W, alpha beta belongs to R, then alpha W1 plus beta W2, it also belongs to W. It implies what? It implies that W is a subspace of R cube. I hope it is clear. So I hope now you are well aware with what you can say. Now you are well aware with what is subspace, what is vector space. Tomorrow we are going to discuss something very important, which is called as a linear combination, basis and dimensions. I hope you will be present in the next class also, and then we are going to take it further to linear transformation, again revisit the eigenvalue problem, also see the inner product space, and then conclude this lecture series on linear algebra. I urge you to keep patience, because all these concepts, when you're going to see them appearing in quantum mechanics, these will make your things quite easy. Even the familiarity with these concepts is more than enough. Okay, I'm teaching you a little bit of higher level, because I want that somehow you should be, at least if you're acquainted with these terms, you should be acquainted with some problems in your head, so that you can you have that sort of familiarity. Okay, I hope to meet you tomorrow. Till then, take care. Bye bye.